Okay, so today we're going to actually try to derive the equation for the area of an ellipse, and we're going to be using integration to do that. Now, quite some time ago before spring break, if you remember, I had you find the area of a circle using calculus integration, and then of course we just recently found the area of an ellipse using integration. But now, instead of trying to find the area of a specific ellipse, I want to find the area for a general ellipse. All right, so instead of like x squared over a number plus y squared over a number, we're going to actually have x squared over a squared plus y squared over b squared. So, of course, the vertices, instead of being located, a certain number from the origin, are going to be a units from the origin, right? Since a times a makes a squared, and negative a times negative a makes a squared, the vertices are at a comma 0 and negative a comma 0. The covertices, similarly, 0 comma b, 0 comma negative b. And just like we did with the ellipse in the previous lesson, to make life easier, I've got some symmetry here. I can figure out just one part of that ellipse, right, a fourth of it, and then multiply by 4, right? This way, instead of trying to integrate from negative a to a, we get to go just from 0 to a. And then instead of the upper curve, subtract the lower curve for the height of each slice. It's just the upper curve, right? Because it's just the distance from the horizontal axis to the upper curve. Okay, so what do we have to do? Well, we got to solve this equation for the variable y. So we need to subtract x squared over a squared from each side. Then we need to multiply both sides by b squared. And then, of course, I can take the square root, and I now have the value for y, right? Y equals the square root of b squared minus, and then the fraction b squared x squared over a squared. All right? Now, we can factor out b squared over a squared, right? Because I need to get the a squared minus x squared alone inside that square root symbol. And you can double check with the distributive property and make sure that this really multiplies out, right? B squared over a squared times a squared. Well, the a squareds cancel, leaves me just b squared. And then, of course, b squared over a squared times that x squared gets me b squared x squared over a squared. Whew, that was a mouthful. And because we've got multiplication happening, right, I can break this up into two pieces. Of course, the square root of a squared minus x squared, I can't do anything with that because they're separated by subtraction. But because the b squared over a squared was multiplied by that other term, we can just take the square root of that and we get b over a. So when we slice this thing up, we know the height of each slice is going to be that expression. We know the width of each slice will be delta x, and we need to go from 0 to a. And then, of course, I need to multiply that whole thing by 4 because I'm just finding 1/4 of the ellipse by doing this. Right? So from left to right, we're starting at 0, and we're going to go all the way over to a. And then we have to integrate with that function. Right? B over a times that square root with all that lovely stuff inside is the height of each rectangle. delta x, or dx, is the width of each rectangle. And because b over a is just a coefficient, and whenever we integrate, the coefficients just kind of sit there and look cute, we can move that in front of the integral. So I've got 4 times b over a times that integral. And there's actually nothing we have to do, because if you look at the generic integral from our integral table, right, square root of a squared minus x squared is exactly what we have. The only difference is, instead of doing the plus c, we've got to plug some values in, right? But I can just keep the entire expression. I can keep a squared over 2. I can keep arc sine of x over a, keep the plus sign, and keep that other fraction. But instead of plus c, I've got to plug in the value for a, plug in the value of 0. Okay, so when I plug in a, right, every place I see an x, I have to plug in an a. So that arc sine of x over a becomes arc sine of a over a. And then that x in front of the square root symbol becomes an a. And then inside the square root, a squared minus x squared becomes a squared minus a squared. Of course, then I have to subtract the answer from when I plug in the other number. So when I plug in 0, arc sine of x over a becomes arc sine of 0 over a. The x in front of the square root becomes a 0. The x squared inside the square root becomes 0 squared. And I do a little bit of simplifying, right? A squared minus a squared becomes 0. A squared minus 0 squared becomes a squared. And at this juncture, I should be able to say, whoa, there is a lot of stuff I can just ignore, right? Square root of 0 is 0. If I multiply that by a, I get 0. If I divide that by 2, I get 0. I can just ignore that because that's just 0. The other obvious one back here, 0 times anything is going to get me 0. I can ignore that. And then the one that's a little bit trickier to see, an arc that gives me a sine of 0 has a measurement of 0, right? 0 radians. And so a squared over 2 times 0 becomes 0. I can ignore that. So all I really have is 4b over a times a squared over 2 arc sine of 1. Of course, what is the arc that gives us a sine of 1? That's pi over 2, right? When sine has a value of 1, we are at the top of the unit circle, right? That's the highest point we can go, right? Vertically, positive 1 is as high as we can go. So remember, sine is the second value, right? So we have the x comma y. We're looking at 0 comma 1, so that 1 will be in the y position. So pi over 2 is the top of that circle. Now, 2 times 2 is 4, and that's going to cancel the 4. A squared divided by a is just going to give me a. And so I'm going to have an a. The b is going to stay there. The pi symbol is going to be there. And so the area of an ellipse is a times b times pi. Right, so that's the area of an ellipse, a times b times pi. Now, if you remember the previous video, when I actually had you find the area of an ellipse, right, this is the ellipse we worked with that was in the video. and we found it had an area of 15 pi square units. Well, if I look at that 25, I'm thinking, well, 5 times 5 is 25. If I look at that 9, I'm thinking, well, 3 times 3 is 9. Right? It's actually x squared over 5 squared, and it's y squared over 3 squared. Well, area is supposed to be a times b times pi. 5 times 3 times pi. 15 pi, indeed, we found 15 pi square units. So that is the area of an ellipse. A times b times pi. Well, guess what you're going to do for homework? You won't be finding the equation of an ellipse. You'll be finding the equation of a circle, right? So the equation for the area of a circle, I should kind of restate that correctly, right? You're not going to find the equation of a circle. You're going to find the equation for the area of a circle, right? So our generic equation, x squared plus y squared equals radius squared. So if the radius is r, notice I've got a picture drawn. The radius is r. Right, so when you do the integrating, you're going to have to start at 0, and then you'll go right until you hit r. And again, I've got just 1/4 of that circle shaded, because the easiest method would be to set up an integral to find that quarter circle, and then just multiply your answer by 4. And so that is what you're going to have on the worksheet. Ooh, diamond plate steel. Looks like I got creative and got some type of a saw and cut out some letters to spell out worksheet from that diamond plate steel. Where in reality, of course, I just clicked a couple buttons with the mouse on the laptop, or it's not the mouse, but that little funny pad on the laptop. And that, did an internet search. That is a black sand beach from the state of Hawaii. I've actually been to the state of Hawaii, and those black sand beaches are like really cool. It's sand that's basically been created by the ocean waves smashing against that lava. Real neat experience if you ever get a chance to do that. If you're wondering about the white sandy beaches, that's not from white rock that's been smashed up. The really, really, really white sandy beaches are from coral that has been smashed up by the waves into tiny, 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 tiny little grains that resemble grains of sand. Of course, most beaches you end up finding like a brown sand or a gray sand because, right, it's the color of the rocks that get smashed up. So if it's a totally white beach, you're not looking at ground up rocks, you're looking at ground up coral. And then for a black sand beach, well, the rock had to be completely black to get smashed up and become a black sand beach.